Yeah. So today we are speaking about gravimetric analysis first up, and then we are going to talk about atom economy. Actually, we'll use a couple of equations that are all connected. We have been working on calcium carbonate in eggshell, and before we came to do this activity on calcium carbonate in eggshell by back titration, we worked at the start of this school year on making chalk. Who remembers what are the two things that we put into the making of chalk? Two chemicals. How we went about doing it. Anyone remembers offhand? This lab. What reagents, chemicals we use, what equipment we use. Anything at all about it?
Calcium chloride.
Calcium chloride, yes. Let's start, Zach. That's a good start.
And what's it called? H2CO3, right?
Well, something with CO3 because you want to end up with chalk, which is what? What is chalk?
Calcium carbonate.
Chalk is calcium carbonate. So let's kind of help ourselves piece things together. I would put the state symbol here. Anyone knows what the state symbol of calcium carbonate is going to be here in this process? Offhand? Do you remember, or would you want to guess? Is it? You think it's soluble? From what you did with the eggshell, do you think calcium carbonate is soluble? It reacted with the HCl, but maybe you didn't have any activity to make you observe if it's soluble. But I'm going to tell you guys that it is insoluble, so then we put S over here as the solid. That means it's not going to remain in water. Other thing that we have in the reaction, and now hopefully you guys, your memory might start coming back. The other thing in here is sodium carbonate. What do you think? That's soluble or not? It's a carbonate now. It's a carbonate, so you might be thinking, what's on your mind? Is it soluble or not? It's soluble. All carbonates are insoluble actually, except sodium carbonate, potassium carbonate, and ammonium carbonate. Yes, Pranav, your teacher made you memorize that before. I made you memorize.
Well, I memorized it after your class.
What? Sodium, potassium, and ammonium carbonate are all insoluble. Are all soluble, sorry, and calcium carbonate is insoluble. So then, what we did was you guys had to get a certain mass. And maybe at that time you were kind of just like following everything like a cooking recipe and not really reflecting on what you did. But now, maybe I want you to look back in your portfolios and go back and see. I asked you guys to put a certain mass of this and a certain mass of this. The mass I remember asking you was meant to be that we would not have anything left over. I didn't want anything left over. I wanted to be that whatever mass of this we put and whatever mass of this would be completely reactive. And if all of this mass and all of this mass reacts together, then the products must match in mass. Mass has to be conserved. It's got to go somewhere. And then we have to have another product over on this side, which is actually a soluble product. If you've already balanced it in your mind, it's 2 NaCl, it's going to be A cubed. Okay? Now, are we remembering the equipment that we used to go about doing this? First, you had to go get a beaker and you dissolved 40 plus 71 divided by 100. I'm doing all of that mentally in my head. 1.11 grams. You dissolve 1.11 grams in about 100 ml of water. I can't remember exactly what was the amount of water now, but you do that in about 100 ml water, 100 cm cube. And then on this side, you dissolve sodium is 23, that's 2 sodiums, 46. 3 oxygens, 48, carbon is 12, that's 60, 106, you divide 106 by 100 and you get 1.06 grams. Remember that we want to put this also in 100 milliliters of water. Both of them are soluble. We put them together and we get them to react, and then we see a white powder kind of just floating around. That is called, well, we are calling it chalk, but it's calcium carbonate. What are 2 other sources of calcium carbonate that we know about?
Eggshell.
Eggshell, yes. What else?
Calcium.
Limestone,
Yeah, calcite.
calcite, limestone, corals. Also, what about marble? You guys have heard about marble? Marble, limestone, eggshell, calcium carbonate, chalk. All of these things are the same calcium carbonate, almost entirely. So this comes out as a solid. Then we take that solid. If you remember what we did now, we're just going back over what we did. And we put it in here. In this device called the Buckner funnel. Right? And we get some suction happening over here like this. And we get all of this going in there. And then we put a piece of filter paper here. And we let all of this filter through. This is connected to a pump. If you remember now, those who were here, Kavya, were you here? Okay. So it's connected to a pump, and then salt water goes out here. If you remember, some groups actually put their beakers outside to try to get all the water to evaporate to see how much salt came out. And then we let all of that thing filter out. And then what did we do with this piece of paper? What did we do with it then? In our experiment, what did we do? You were here for the experiment, Nikhil, at that time? This experiment, you joined this class late? Can't remember. You were here, Rihanna, for that experiment? Ria, you remember being here for the experiment with the funnel and the making of chalk? Right, well this is the whole thing. You should have it on your portfolio in case you don't remember it. The portfolio is, it's like, how many of you have heard about something called the family album? You've heard of it? Family album. Yeah. Family ALBUM album. It's not like a music album, you know, it's like with lots of pictures in it, right? The reason I asked if you heard about it is because, well, when were you guys born? Like 2006 or something like that, right? Yeah. Everybody had a digital camera device or whatever. Who keeps a family album, which is a place where you keep like hard copies of pictures, like you stick it on a surface and you put like a plastic cover over it. You have anything like that at your house there, Kavya, from your grandparents?
Yeah.
Your parents?
Yeah, both.
Your parents might have some. Most likely grandparents will have some precious memories there of your parents. That might be fading. If it's fading, what you can do is to like take it out of there, take a digital image of it and get it enhanced somewhere. You know, that's what you should do to save it. Because in time, all of these things could actually fade. So then you could save it like that for yourself. But look at what has happened with photography, right? Photography, which was a tool, very important thing. Somebody is a photographer, then they have to go to the dark room and develop the photo and everything, and you have to, that has become like something that is extinct. But again, in school, what exam students were sitting for when World War II ended? 2 hours of exams, paper and pencil, you submit to the examiner. You guys are submitting the same kind of thing still today. So it's not good. But this experiment here that we are doing right now, for that matter, we have to ask whether it's of any purpose or any use. If you wanted to find out how to do this experiment, you could find out all about it, watch a video, make a video for yourself for that matter. Then you could order a robot to carry out the experiment for you. Okay? In the sense also that the robot could be sitting in this lab and you could be sitting at your house. Then you could have something in your hand that says pick up funnel, place funnel in there. And you don't even have to talk. You might be dragging something, put the funnel here, and then the robot gets that instruction and literally it comes here and it puts the funnel up here. Now that is not something that's in my imagination. There are robots running on Mars that are being controlled by NASA right now. Okay, but you guys are coming here, taking the bus every day back and forth from your house, and you get up in the morning. You don't really want to come to school, but you have to come because you are coming to school in the time-honored way that people have been coming for hundreds of years to school every day to learn. Okay, even though robots are being running on Mars, right? So you come here and you let this filter, and you set it up, and you find your mass of calcium carbonate. Okay, so what mass of calcium carbonate would you expect? You subtract the mass of the filter paper. What mass of calcium carbonate are you expecting here? And how can you calculate that? This is where I want everybody to pay attention. This is where we are getting back now to our gravimetric analysis, and we'll talk about yield, which is the important thing, alright? So tell me, how could we predict the mass over here? Yes, sir?
So you divided like the number of moles by 100, and like that's how you got your value graph. It's like you divide your MR by 100.
Okay. Sometimes students come through the whole of IB chemistry and they're still, you ask them, why do we balance an equation? If you don't know why you balance an equation, then it's something to know. Otherwise, it's not just something that people are doing so that they will look fancy and intelligent and say that I'm doing chemistry. It's got a purpose behind it. It can't be in words, because people are then able to predict. If I take 0.1 moles of this, 0.1 moles of this, I will then expect 0.1 moles of this on this side here. And then I can use what to predict the mass? The expected mass. The theoretical mass from that calculation. That theoretical mass or theoretical yield would be equal to this amount in moles here, and then the MR goes down here. So you'll have to use that equation to figure out the mass in grams. Okay? And using that equation over there, we will say that MR multiplied by N, the amount in moles, will give us the mass in grams. MR of calcium carbonate, again I can do that roughly in my head, it's 100. Calcium is 40, carbonate is 60. 12 for carbon and 16 multiplied by 3 for oxygen, 48. 100. So then 100 multiplied by 0.1 will give us approximately 1 gram. So using that 1 gram as the theoretical yield, okay, you write that down. 1.00 grams. The 0.00 that I'm putting here, of course, is based on the fact that I have a balance somewhere that's giving me 2 decimal places. If it's not giving me 2 decimal places, then I can't put that down. Then I should also put plus or minus that over there as well, to show that I have acknowledged the uncertainty associated with it. So now that we carry out the actual experiment, Chinmay, did you carry out the experiment with your group? Suppose we carry out the actual experiment and it comes up that we found the experimental yield now equals 0.91 grams. Again, I would write plus or minus 0.01. Okay? 0.1 is the first digit, 0.01 is the second digit. I'm just using plus or minus the amount of the second digit. That's one way to do it. Also, you can take plus or minus half of this second last digit, which would mean that this would be 0.5. Okay? Let's do it like 0.5. Okay? But if you go with 1, in fact, if you go with 1, that might be what the balance says to use. When it's a digital device like this, you might go with that. When it's an analog device, you know, one that has readings on it like a burette, you take plus or minus half the smallest division as your uncertainty. Those are things that you'll have to pay attention to in your lab. Okay? So, we've got experimental yield, we've got theoretical yield. Then, how do we get percentage yield? Isn't it kind of like logical what we do?
Divide the experimental yield by the theoretical yield by 100.
Right. Okay, so then we say experimental yield divided by theoretical yield will give percentage yield for the experiment. And that will be 0.91 divided by 1 multiplied by 1, which will come up to 91%. So let's say you do this experiment, right, and you get a yield of 91%. Should you just leave it like 91%, or should you write something after the 91%?
Plus or minus.
Right, and again, for calcium carbonate in Excel, which you guys are working on, you will have to also have a plus or minus in your answer. So you put plus or minus some value here, which is based on the propagation of this error and this one. This 0.01 is 1% of this. I can see that mentally. And it's about, of the 9.1, it's about like Again, about 1.2% or something like that. So those two percentages added up would give us plus or minus 2%. Plus or minus 2% because once uncertainty goes above 2%, we don't attach any decimal places to it. We bring it to the nearest whole number. So if it's like 2.1 or 2.2, we leave it as plus or minus 2%. If it's less than 2%, we can have it like with a decimal place behind it. Okay. So this would be the uncertainty. This uncertainty here that I put here as the propagated uncertainty, what error is that based on? Random error or systematic error? Random error. You see, random error is when the balance over here, when we put our filter paper to find the mass, and we're getting some mass in grams in here. When we do that, that is random error. Because it's what we say when we do this is the mass could go above or below. A burette also has random error. Pipette has random error. The balance has random error. So there are several steps in your experiment. The volumetric class has random error. So there are several steps in your experiment which have random errors in them. Alright? And you want to focus on those random errors and gather all of them together and find out what is the final uncertainty with your experiment. Now still this plus or minus 2%, where is the other 7% that you didn't get? Because you know, you still only, if you say it's 2% this way, right, that you lost because of the balance. Where's the other 7%? Where's the other 7% in the experiment? Where's it gone? Any idea, Kavya? Nikhil, any idea where the 7% is gone? When you guys did this experiment, you know, it's like, wasn't it that some people were seeing a cloudy substance down here that you were not supposed to see? Did that happen to your group, that you were seeing some chalk actually seep through the sides of the funnel and whatnot and get down in here? But that's the type of error that you could avoid if you think about, you know, doing your experiment different. You could avoid it. And you could fix it in some way. But still there might be some seepage happening. Okay? So that kind of error that is continuously going to push your result so that you get less mass here all the time. If it is that mass is going through the sides of the filter paper and going down into the flask, always you are going to be getting less mass than you are supposed to get. That is the nature of systematic error. It's not about if it's a system or if it's not a system or anything like that. Systematic errors push your results consistently in one direction. Random errors can push your results above or below. Systematic errors cannot be fixed by repetition of the same procedure over and over. If you are using the wrong size filter paper, always it's going to seep through. If you ask for a bigger size of paper and you wet it on the ends and you seal the corners, you might have helped to fix your systematic error. Systematic errors can be fixed. But what about your balance? This plus or minus value that we have, the manufacturer has said it comes with that uncertainty. You can't fix that. But it goes above or below. Random errors can go above or below. You can't fix them. You can do more trials to kind of average them out because they're random. One trial you might have a plus 0.1, the other one you might have a plus and minus 0.1, and they can get averaged out. So random errors can be addressed by many trials. Values can go above and below. Systematic errors, if you don't fix what's wrong, it's going to be over and over the same. It can be fixed by you reflecting on the procedure, changing the procedure to some extent, and it always shifts your result in one consistent direction. Suppose somebody came and dumped some chalk into your experiment without you looking. That is like that you wouldn't call that any type of error. That's really like serious problem. But it would lead you to having more than 100%. Okay? But imagine you did your IA and then you wrote up in the sources of uncertainty, right? That so-and-so student came and dumped chalk just because they don't like me. Nobody would accept that. You have to put errors that are reasonable, things that you genuinely, within reason, cannot fix. Okay, so like if you have a small size filter paper here, and your funnel is big, and you say, well, my paper was too small, I didn't have a bigger paper. That too might sound reasonable to a student, but it wouldn't be. Because couldn't you ask for a bigger paper? You mean your school cannot afford to buy you a bigger piece of filter paper? If it can't afford, at least you could get a coffee filter or something and put it there, and it would work. Okay? So your errors have to be meaningful. It can't just be things that you are pulling out of thin air. And you only get insight into these meaningful errors when you carry out the experiment yourself. Okay? So I want you guys to go pay attention to all of what I spoke about here. It's in the book. So now I want to talk to you guys about the second thing today, and then I'll give out the test papers and whatnot. The second thing today I want to talk about is atom economy. Previously in IB chemistry, atom economy used to be a part of option A. And now it is a part of the main syllabus because there are no longer any options. And it's a pretty simple thing. The formula for atom economy is inside of our data booklet here. And it's also in the textbook there. First page of the chemistry data booklet for first exams in 2025, a brand new data booklet. Under section 1, it says percentage of atom economy is equal to the molar mass of the desired product divided by the molar mass of all the reactants. Okay, so that's your percentage of atom economy. Molar mass of desired product. We'll just use this abbreviation. Call it useful products divided by the molar mass of all products, of all reactants. And we multiply that by 100. For this experiment here, what is the useful product? If it is that our goal was to manufacture calcium carbonate or to make chalk. By the way, this is not how people actually would be making chalk, right? But if our goal was to make chalk with this experiment here, what would be our atom economy? Can someone tell me what would be our atom economy here? What would we be doing to find the atom economy? Pranav, you can see. If this is your useful thing that you want, what would go on the numerator? The F, the molar mass of calcium carbonate, which is about 100. Then down here you'd have the molar mass of this plus this, which we've already worked out today, right? It's 111, 106. Multiply by 100. That's your atom economy. What's the point of calculating atom economy? It's a measure that was introduced by chemists not too long ago, about 30 years ago, especially when we are thinking about environmental impacts of various processes. You want your process to be measured not just in terms of the yield, which we just looked at how to calculate the percentage yield, but we also want to look at the process in terms of the atom economy. And the higher the atom economy, the more efficient your process is. So the atom economy here, you could use this as an example. Last night I put on Google Chat another example with the manufacture of cement. Calcium carbonate doing what? Heating, getting heated, right? And producing CaO. And what else? CO2. This is an important step in the manufacture of cement right here, you guys. And this is where people consider atom economy a lot. We might be thinking, okay, what are the sources of fossil fuels out there in the world? Of carbon dioxide in the world? And people would say fossil fuels, the burning of coal, oil and gas, factories, cars, trucks, buses. What a lot of people don't know is that this manufacture of cement, which we use a whole lot of. Right now here in Bangalore, we're using a lot of cement every day, right? Yes. You look at all of where they're building the metro, where they're building this overpass, this road, the next building, that building. A lot of calcium carbonate is being used. And people might be thinking, okay, the cars, trucks and buses on the road are the things putting CO2 into the air. But cement that has to be made has to be heated to a high temperature. How is the cement heated to the high temperature, by the way? This right here. How is the cement heated to a high temperature? Using what? Using some kind of kiln or oven or whatever. And that might be using what? Fossil fuels, coal, oil and gas to power it. So getting the cement to be heated up, the calcium carbonate, to be heated up is one thing. And then when it produces calcium oxide, which is one of the steps, all of this is waste. So a way of kind of quantifying and measuring that amount of waste is the concept of atom economy. We could say the atom economy for the first step in the manufacture of cement is so much. And then we plug this data into this. Atom economy is something that is related to the environmental impact. It kind of gives us a measure of how much, it's kind of related to yield. It's very much related to yield, where you get how much of the product you want divided by how much you expected. But here, it's how much of the useful product you get compared to the mass of the reactants. And in a sense, it's also by default taking into account the thing you don't want. How much of that? So the higher the percentage of your atom economy, the more environmentally friendly then your process, because it means less mass is going out as waste. If that waste is CO2, it's very concerning. Whatever it is for that matter, it could be some pollutant that goes into the water, something that goes into the air. In addition to it being a waste of mass, it's useless mass, and it's going to add to your cost. It might then on top of that have an environmental impact. And it's a pretty simple equation, but atom economy is an important concept.